Good morning. This is session 7 of the ETH course on mathematical methods of signal processing. And I'm working from the file prepared for this course, specifically ETH test A, which is in the current version of what we will see on the screen. The main point and the goal of this course will be to tell you that there are many different ways of defining convolutions, and that these different ways can be all taken as one convolution with different domains. And so we are gaining a lot of flexibility from kind of this week on. We will use the star symbol for convolution in every context, but we are justifying today that this is really the same star, very much like the multiplicative sign for rational, irrational, or even complex numbers. It's always the same multiplication, and if the result happens to be in a smaller space, like it happens to be rational, we're happy with the result, even if the computation was done in the larger domain. So the first step with a recapitulation of what we have done so far, and I'm not sure, maybe some parts are not discussed in the video, but only in the course notes, is we have seen by analogy to the polynomials that translation invariant systems can be stored in a very efficient way. You just need one linear functional. Now we have chosen in our case now the space C0 of functions which are continuous complex valued vanishing at infinity with the sup norm. It's translation invariant. It allows the flip operator, which is taking the inverse argument. And there is a nice connection. The operator, which is a translation invariant linear system, I call it T mu, induced by a measure, by a linear functional, is obtained pointwise by mu applied to the function, which is f flipped, then shifted by the argument y. So it's ty f flipped. Or you could say it's t minus yf and then flipped. Okay, or if you're having a system and you're asking how can I retrieve the corresponding generating linear functional, which is a bounded measure now by terminology, you just have to insert the flipped function. The output t of f flip is a continuous function which has a value at 0. And this is the most important connection that we will use all the time. Now it can be used to show that the size of a system generated by measure is controlled by the size of the measure as a functional. And if you do some calculations, you are finding out that this is really a system which is linear, bounded, and commuting with translations. We also were showing that it preserves continuity. Actually, it preserves uniform continuity, not the pointwise continuity. And then there's an important argument, and I hope I have done it. If you have compactly supported measures mu and compactly supported functions f, we will describe this in more detail later on, but you can think that everything is concentrated in a bounded set. So for example, mu is a linear combination of Dirac measures, and finite Dirac measures are living in some ball of radius r. If the function f is living in some ball of radius r as well, by symmetry you can assume that the same r, then this new system, so that you will say the convolution of mu with such a side condition with f will be 0 for y outside of the ball of radius 2r. And I just want to show you the key argument. Of course, we split the functional, the measure mu, into pieces mu psi I. We split the function f into pieces. So we only have to check what happens with the system introduced by the little piece of mu applied to a little piece of f. And if you look and apply all these formulas on the very right-hand side, you see in the square brackets, there's a product of psi I with a shifted version of the flipped psi j. Now, if you think of a little bump function psi I and another bump function psi j, maybe also flipped, and then you shift it far away, it's clear that these two bump functions have nothing in common. Their product will be 0 because either you're inside the ball of radius r, then this one may be non-zero, but then the shifted second one will be 0, or vice versa. If you're outside of the ball, then maybe this is non-zero, but definitely psi I is 0. So if you take the square bracket 0, multiply it with anything, it will be 0, so mu of this will be 0. So we are getting that T mu of f under this extra assumption, and I'm looking back, this extra assumption was finite sum of these pieces, will give you a function with compact support. Now we also know that if you take more and more pieces of either mu or f, and so larger subfamilies, then this will be convergent, and you use the continuity of the action, the control of the system by the size of the measure times the size of the function, in order to find out that you have limit of functions in the compactly supported things which are still in C0, because C0 is a Banach space. So you see the completeness is very valuable here and in many other places. So altogether, to summarize it, we have two relationships. One is making from a functional translation invariant system. At the moment, it's called T mu. In the script, it's called C mu for convolution operator. And very soon, we will just write mu star f for this. And I also told you that the flip operator is only important in order to have the convention that if you take a Dirac measure, you would like to have that the convolution with a Dirac at 5 is a shift to the right and not a shift to the left. Therefore, we have to have this slightly disturbing flip operator all the time, and very often canceling it. Another thing is, and that's the big difference between discrete and continuous signal processing. In the discrete setting, every kind of functional is more or less an infinite row vector, and the row vectors are also signals on the discrete setting are sums of unit vectors. And unit vectors are just shifted versions of the basic unit vector at 0. So you can say that everything is understood once you know what a system, translation invariant linear system, is doing on the Dirac measure. Now we cannot do the same thing. We can say we take linear combinations of point measures. These are the bounded discrete measures. So if the sum of the coefficients is finite, everything is okay. But they are only constituting a closed subspace. So we don't reach all the measures, and so we have to work a little bit harder to verify that somehow in a different way, discrete measures approximate the arbitrary linear functionals. Of course, you know one very good example, the integral from a to b of a function f, which is continuous on that interval, is well known by Riemann integration theory as a limit of Riemannian sums. And it's very easy to write Riemannian sums exactly in the form that we have. You have delta of psi I in the Riemannian business. Psi 5 is the, let's say, the midpoint or one of the points in the fifth interval of a Riemannian sum. And the mu of psi I, you just take the rectangular function, it's just the length of the interval. So we are doing something slightly more general, which actually works also for locally compact abelian groups, and define a discretization operator starting from a BUPU. Please think of psi I being a system of triangular functions or B-splines, a collection of functions which have all small support. They're adding up to 1. And so by retrieving the coefficients, which is applying the linear functional to the continuous function psi I, is giving you a number. If it's a positive measure, you get positive numbers or non-negative numbers, and these are the amplitudes. So the discretization operator is this, but it has the very important relationship to the spline interpolation, spline quasi-interpolation operator, which I call SP psi. And again, for the triangular system, SP psi of f is just what MATLAB would plot. It's the piecewise linear interpolation of f along a fine lattice, a grid in the linear space. Now, We all know that these piecewise linear interpolations are approximating the function in the uniform sense for every f in C0. And therefore, if you apply mu to the spline operator, and this is an exercise which we have done already, is the same as the discretized measure applied to the f. This will go to the mu of f for making psi fine enough. So that's exactly, again, the spirit of Riemannian sum. If the Riemannian decomposition of intervals of AB is fine enough, the number that you get from applying a Riemannian sum formula is almost the integral, which in our case is now an abstract mu of f. We also have the fact that SP psi of f is a shrinking operator. So you are controlling the size of d psi mu on f by checking the size of the functional mu times the size of the quasi-interpolation. And this is not larger than f. So we know that d psi mu is controlled by the size of mu as a functional. So once we have this situation, we have really a very nice storage of translation in all the information about the translation invariant systems by storing the linear functional, or by describing the linear functional. And as we will see, it's an approximate description by using the discretized version d psi mu, but that's the story coming up. What is important is that we have to define a kind of multiplication which matches the composition of translation invariant linear systems. So recall again the situation with matrix multiplication. We have a storage of linear mappings from Rn to Rm in the form of m times n matrices, and we do matrix multiplication. But then the composition of linear operators must correspond to some kind of multiplication between matrices of appropriate size. And this is what we learn in linear algebra courses, how to do it practically. Now we are doing it in the same spirit. We say the convolution of two measures mu1 and mu2, two bounded measures, is the linear functional which describes the composition of the two convolution operators. Recall that at the moment we are having no statement about the order. It may be important to keep the order of the operators in the symbols of the convolution. So for the moment, we use star mostly to describe this internal multiplication. And then, of course, formula 51 is quite easy to understand, because for operators, the magnification that an operator has is the operator norm. If you compose two operators, one with magnification at most 3, the other with magnification at most 5, it's clear that the composite order will have at most magnifications 3 times 5. Okay, so we have this just by transfer of operator equations back to the linear functionals, and the star corresponds to composition of systems. We also know that the operator norm of this operator is exactly the norm of mu. So in practical terms, we will use all the time mu. And now it's a different convolution. You have to see it's the convolution operator applied to f. It's not an internal multiplication, but I'm already starting to write it in this way. And because it will be useful later on, if we want to understand what mu of f is or how it is connected to this kind of extra convolution between measures and functions, so it should be viewed as an other form of multiplication. So it's like multiplying a real number with a rational number and saying, well, it's clearly a real number here. It's kind of a signal. And you have to apply the convolution operator by mu to the flipped function and evaluate at 0. I would say that the red representation is clear because you cannot apply a convolution operator to the value f flipped at 0. So it wouldn't be meaningful to read it in this way. But to make sure at the very beginning, I'm saying, well, this is form mu convolved with f flipped. So apply the convolution operator to f flipped. the resulting continuous function has a value at 0 and you evaluate it, and this is the linear functional that connects this. Now, I would like to tell you many different things, and many different things in the sense of many different ways of describing convolution. So it was one of my PhD students who was reading an early version of the script and said, well, in the books I find this formula 54, mu convolved mu1 with mu2 at f is just a double integral. So if you have a measure, you can form the product measure or the iterated measure according to Fubini, and you apply it to f of y plus x. Now, clearly this function at every point x, or every pair x and minus x will be the value at 0. So this function f maps x and y to f of y plus x or x plus y is not decaying at infinity. So at the moment I postponed this discussion a little bit, maybe I even don't do all the details, because one would have to prove first that this bounded continuous function can be integrated in this way. Our argument will be essentially this: mu1 and mu2 are objects which are mostly concentrated on compact sets. So cutting off the tails of this function doesn't matter. Every truncation allows you to apply it. And so this is a bounded and continuous function of two variables. Tensor product of the measures is fine. And so we will see that this is another form which is only in the current version reasonable in the spirit of measure theory. That's why I don't want to do it so much. Now, going back to the deep psi operator, I was already telling you that this is in the middle of the screen now. Deep psi mu of f goes to mu of f. And of course, it's not only for f. You can take f flipped. You can take a shifted version of f flipped. And so now going 55 says, we have this kind of convergence. This discretized measure applied to individual f goes to mu of f. The point is that you have to know the f if you want to have an epsilon approximation or the quality of f. It's again like Riemannian sums. A very nasty continuous function may require a very fine partition of the decomposition of the interval. But it doesn't matter. Eventually, every such function f is uniformly continuous, and that is good enough to guarantee this, because then these spline approximations will be close enough to the f. As I said, you can apply this pointwise, and then you see that the convolution of the discrete measure minus the convolution of the measure mu will go to 0 for every point. So this statement says, you're giving me the f, the measure, and the point where you want to control it, and then I can tell you how fine you have to do the job. Now there is some easy compactness argument. If you give me finitely many y, well, if you're asking me to do this for a whole interval or a compact set, you're approximating the collection, this infinite collection of y's by finite collection, and you make epsilon estimates, everything is fine. But the true thing is, or the interesting thing is, that you can even have it uniformly. So you don't have to tell me where you are going to test it. You're just saying, well, here is the measure. And somehow, is the measure. And then I'm finishing the sentence. And then here's the f. And then I'm telling you how fine the partition has to be such that you can guarantee this epsilon approximation. Okay, there was the question of this convolution is, as you see, a measure convolved with f. So it's the operator, which is the system introduced by the functional. We have modified the functional to the deep psi mu. So these convolution stars are action of measures on these things. So essentially, it also tells you, I mean, clearly the deep psi mu is a bounded discrete measure coming from the bounded measure mu. And because this means it is an infinite sum with coefficients which are absolutely summable, you can approximate it by finite sum. So this also tells you any system can be simulated if you're only interested in one or finitely many specific input signals, or actually a class of signals which have equal quality in terms of equicontinuity, but that's a bit too far now, by a convolution with coefficients. And these coefficients are drawn from the measure, the functional. So they are big at the places where there's a lot of mass in the measure concentrated, so where the mu psi I is significant, whereas it may be harmless or very little in the places where mu is small. And of course it will be zero in outside of the support of the measure, but we have not defined this concept yet. Now, why is this important? Because our next goal will be to prove that the convolution is a commutative procedure. So it doesn't matter which system you apply first. I mean, if you take it from the point of view of systems of black boxes, it's absolutely not clear why you can change this order of boxes applying systems. If you look at the convolution operator, you say, okay, can I convolve mu1 with mu2 and get the same as mu2 with mu1? And now for this, as an approach for this, I'm saying, well, take the discrete measures. And remember, this is the closure of the linear combinations of Dirac measures. So it's the infinite sums of Dirac measures, which are absolutely convergent in the measure algebra. And this is a commutative algebra. And this is a very harmless consequence of the fact that we have seen already a Dirac delta corresponds to a translation operator. Therefore, the correspondence between measures and translation operators means delta x convolved with delta y. This is now an internal convolution of measures, is the system which corresponds to Tx composed with Ty. And we know this is, of course, translation by x plus y in any order. And that's why for Dirac measures, the convolution or operation, the composition of translation operators doesn't change if you change the order. Of course, you do this for finite linear combinations. You're taking limits and you're doing it for infinite linear combinations. So for infinite discrete bounded measures is no problem. That's why we have this statement. It is closed. If you take limits, you're not getting out of this, which also means you cannot approximate a nice linear functional with a density from a test function, so this mu sub k that we have seen out already, by discrete measures. So it's a little bit too narrow, or the norm convergence that we have here, this size of a measure is too delicate. We have also seen that if you let xn go to 0, the delta xn minus delta 0 has norm 2, because it's two different Diracs, one with a sign coefficient +1, the other -1. And the sum of those two absolute values is always 2, even if the xn is very, very close to the original limit 0. Okay, so we have this, and therefore we want to show now for the general, in the general way. And we will use this approximation principle to get this commutativity. So in terms of operators, the proposition 2 says the composition of two invariant linear systems does not depend on the order in which you apply these systems. Now, the proof that I will give you is an indirect one. Assume the convolution, internal convolution of those two bounded measures might be not the same, at least for one example where you happen to have some counterexample. So I will show you that any counterexample will lead to a contradiction to what we know already. If the two measures are different, you have to distinguish their action on some of these functionals by choosing some f. And of course, you can assume if it's non-zero, by normalization, it will be a function f of norm 1. And then the difference must be some positive number. And actually, this is not good because it shouldn't be, I mean, I have to correct it. It shouldn't be the subnorm. It should be the absolute value. I'm applying a functional to a function f. So I'm getting a complex number, and so on. Now, I will probably have to rewrite this paragraph a little bit, but you have it here, and therefore we discuss it. Now, the idea is very simple, and I will have this in this next lemma, that also the deep psi mu will minus deep psi mu1 convolved with deep psi mu2 applied to f will be small, again, in terms of absolute value. This is a consequence of what we have know about the discretization operators, but not in the form we have discussed so far. So again, I have to correct this. And the same with absolute values with this. Now, if you put these things together, then you get that the absolute value of these, because here we can change the order. So remember, the deep psi mu1 and the deep psi mu2 are discrete measures. So these things are equal. So the difference of the close by elements must be at most epsilon over 2, or epsilon 0 over 2 would be more correct. Whereas we were assuming that it's epsilon 0. So if you do a good enough approximation with discrete measures, you have a contradiction. So, okay, I'm sorry, the write-up is a mess, and I will have to do it, correct it now. But the consequence is now important. So we have that the measures are a Banach algebra. We can convolve them. They are complete space. And the norm of a measure convolution, is controlled by the product of the norms. So I'm starting to, maybe I'm skipping this for now, because I think for me it's better to recall another approach. So my approach to convolution was through systems, and I think that's the important natural approach for engineers. Engineers have to learn about convolutions and Fourier transforms because they want to understand translation linear invariant systems. All the other things are kind of mathematical objects. We are defining convolutions for functions. We are defining the action of a convolution operator on a function, all these things. But if you take, for example, Hans Reiter's book, he was my advisor, then he would say, no, we have to start with the algebra L1 of Lebesgue integrable functions. And there, this formula of pointwise, I call it pointwise multiplication. You can say, okay, another new operation, a new star is born. But it's pointwise convolution of two functions. And it's this formula, k1 of y minus z times k2 of z dz, and you can change the order. So here, by simple substitution, everything is fine. So I will use this formula only for Riemann integrable functions. So for test functions, k1 and k2, which are continuous, then the product is also continuous, is living in a compact domain, and therefore it's Riemann integrable, and we have this relationship. But before doing so, I would like to go to tell you a little bit, and it's kind of informal if you want to do so, do some storytelling for the rest of the first part of this session about Lebesgue integration. So it's really one of my goals to say Lebesgue integration is great. You're getting a Banach space of Lebesgue integrable function. Later on, you even get a Hilbert space L2 of square integrable functions. You have Plancherel's theorem, which shows that the Fourier transform is an isometric, even unitary mapping or energy preserving mapping on L2. So why does he avoid L2, the Lebesgue integration theory? Well, because it's quite cumbersome, and at the end, it will not allow us to take a Fourier transform of even constant one. So certain things that you want to do definitely in engineering, or for example, sampling and so on, cannot be done properly with Lebesgue integration theory. Also, harmonic analysis or Fouille analysis is properly done on locally compact abelian groups. There one has something like the Riemann integral, which is called the Haar measure. From the Haar measure, you produce measure theory, you get L1 of G, and we define convolution, you define a Fourier transform. All this can be done, but I find it much more natural to do also the same approach that we have done so far in the context of these general groups with translation invariant systems. But again, this is not the point of my representation. So the first thing is I want to justify my use of the notion of a bounded measure. So in measure theory, you have measures which are sigma additive things which allow you to measure the size of a set. Well, in order to avoid contradictions, one has to restrict the collection of measurable sets, so avoiding pathological sets, and then derive the notion of an integral. So you get from measure theory expressions like an integral over such a group of a function f of g according to a measure d mu of x. And how does it go? Well, if the function is a step function, and boldface ak means it's a constant one on a subset ak, let's say a subset of finite measure, and ck is the amplitude. So think of a collection of box functions, n box functions with coefficients ck. Then of course you know how to integrate it. You would say it's the size of the basic, so it's the volume of this set of ak, the measure mu of ak, times the ck. It's the whole business of measure theory that you're saying, well, we know, or we start from the idea that we know the volume of parallel epipeds. So think of rectangles in the plane for two-dimensional situation, d equals 2. And if you know the volume of a cube, then which is just the product of the side lengths, then you can shift it around. You can build sets which are collections of such cubes, so Lego kind of figures, and you approximate a measurable set from the inside and from the outside. So you're able to measure more sets, you have more step functions, and then by a delicate limiting process, you're defining an integral for positive functions, which is either plus infinity or finite. And then a measurable function where this integral, also called L1 norm, is finite, is called a function in script L1. Now, you would like to say this is a size measurement, but of course a function which is zero only on a set of measure 0. So for example, if it's non-zero only, if it's non-zero only at finitely or countably many points, or a very thin, even uncountable set, then it would have this semi-norm equal to 0. And that's why you resort to this idea of take equivalence classes. So the script, the Lebesgue space L1 of R is in mathematical courses well described vector space of equivalence classes of measurable functions with a finite L1 norm, and you define all the things that you want to define, like convolution. But of course, the problem is here that if you write the convolution integral in this level of generality, it will exist almost everywhere. But that's good enough to show that it represents one class. And so you have a symbol for f convolved with g. Now for Lebesgue integrable functions, it's representing another class, and so on and so forth. So it's a rather delicate thing. Now, if you start from Lebesgue integration theory, you get a number of facts. The first one is it is a Banach space. And that's very often taken as a key argument why one should use Lebesgue integration theory. I was using the duality to get the bounded measures, and we will see that we can define L1 as a closed subspace of the bounded measures. Therefore, it will be also a Banach space. It's important to prove that the continuous functions with compact support are dense. Now, very often this is done by saying, Well, you approximate an L1 function by compactly supported L1 function, and then you smooth it out by convolving it with some test function. But in order to allow this argument, you prove that continuity translation is continuous in L1. And if you use this, then very often you're using the fact that the continuous function with compact support are dense. So that is almost a circular, vicious circle. So one has to resort to a more cumbersome approach to say, well, we approximate an L1 function by step functions. Measurable step functions are approximated by ordinary step functions. An ordinary box function is easily approximated by a continuous function if you think of a trapezoidal function in 1D and multidimensional. But you see, it would be a lot of work to do this in all detail. I've already mentioned that convolution is well defined and satisfies the expected equation, inequality, the submultiplicativity. We can define the Fourier transform, and if you say, for me, the Fourier transform is an integral transform with a complex pure frequency e to the minus 2 pi I omega t, and I use the 2 pi in the exponent, then of course the absolute value of the integral is the same as the absolute value of f of t. So it's exactly integrability which makes this integral work. And we will discuss, we don't need integrals to define the Fourier transform, that's the key. Also, Fubini, a well-known part of integration theory, allows you to prove the convolution theorem. So I should have written, it's the L1 convolution here, which allows you to take a Fourier transform, which is a bounded continuous function vanishing at infinity. That's the Riemann-Lebesgue lemma. And then you have the product inside these continuous functions, and this is the convolution theorem in the context of L1. Okay, and the Fourier transform is even invertible, but there's another catch in this story, because you cannot guarantee that the Fourier transform of an integrable function is integrable. Therefore, you have to say if, and in brackets, you are lucky and find that your Fourier transform f hat is also integrable in the sense of Lebesgue, and it's always continuous, but it may not decay well enough, then you can recover the function. And from your signal analysis courses, you know, if you take a box function f, it's clearly integrable, even Riemann integrable. Its Fourier transform is a sinc function, which is not in L1, and still, of course, you would like to come back. Now, technically speaking, there are two things, or at least one thing that I think is very important, and why the completeness is coming in, and that's the so-called dominated convergence principle. You will also see, I will not make use of it, but it's very often cited and used in standard mathematical books on Fourier analysis. So it says essentially you can have pointwise convergence, then the integral, then the functions, then the functions are also convergence in the L1 norm. Now, there's a very easy example. You take any function, for example, a Gauss function, and you shift it to infinity. Then, of course, at every point, the function fn shifted, let's say by n, will be smaller and smaller. So you move your bump function to infinity. In that case, of course, you don't have norm convergence because the limit will be 0 and fn, L1, all the shifted Gauss function would have the same norm. But if there's a dominant function, so if there is any function fixed g for all the n, it dominates these integrable functions in the pointwise sense, at least almost everywhere. And if you have pointwise convergence, then you have norm convergence. So this is one of the very strong and often used theorems referring to. But as I keep emphasizing, this integration theory point of view, or the point of view, in order to define convolution, in order to define the Fourier transform, we have to take the integrable functions. It's fine. Okay, yes, thank you for the comment. Of course, this G has to be in L1. So if there is a dominant function which is controlling all these functions, You're right. Otherwise, I could take constant 1 for dominating all these shifted Gauss functions, and the conclusion would not be valid. Yeah. Thank you very much for the comment in the chat. I will maybe tell you only a short comment before going into the break. And that's the number 1 property here. How can you, I think I've typed it in somewhere, but I can tell you in words what I'm having in mind. So how can you relate what we have been doing to the L1 story? We have seen that the continuous functions with compact supports, so every k in this space introduces a functional mu k, and it's by integration of your test function f of x against k of x dx. So essentially, measure theoretically would write d mu of x equals k of x dx, and you would say k of x is the density of the functional. It's an absolutely continuous functional. Now, if you take all of these nice measures with continuous density with compact support, then you can try to take the closure of all of them in the bounded measures. And because you have a subspace in a normed space which is complete itself, the closure must be a closed subspace, and that means it's a Banach space itself. And this will be our definition of L1. Now, in the case of discrete measures, we have already mentioned that you get the closure of a subspace by taking the absolutely convergent sums. So if you take absolutely convergent sums in the spirit of the L1 norm with the Riemann integral, or it's equivalent, as we have seen already or indicated by our pictures earlier on, if you take them absolutely convergent in the bounded measures, you have kind of functions with finite, let's say positive functions with finite measure under their graph, and you pile them up. And then it turns out that they will be finite almost everywhere. So you cannot have a rectangle plus infinity on a set of positive measure by adding up an absolutely convergent series. So in a way, you can use measure theory to say, well, an absolutely convergent sum gives you something which you understand from the measure theoretic point of view, from Lebesgue integration theory. It gives you something which is finite almost everywhere, which actually has an integral, which is the Lebesgue integral. And so we will see that for us, the Lebesgue integral is just an extension of the ordinary Riemann integral to a closure in the bounded measures. And therefore, we are saving the idea of working with sigma additive measures and measure theory and so on. But I would like to tell you, it is the same. You're not getting a different thing. It's just a different fabrication of the same object. Again, you see here, I have used a star for pointwise convolution, but in the spirit of L1 of Lebesgue. We had it before pointwise for continuous functions. And so I will spend time after the break to explain the different versions of convolutions. And if you have questions, I will stop the recording now. Then please let me know and in the chat. Thank you. I suggest I don't know, maybe a 10-minute break so that I can start at 9:10. Thank you very much. So in the meanwhile, I was browsing the script and found that what we have been using already is coming up later on. But before, let me slowly dive into the use of the symbol star for convolution. So later on, we will use quite often this formula number 80, which I put in green. And here you have to be very careful. So there are 4 times you see a star, but on the left-hand side, you see it's a concatenation between 2 bounded measures. So this is this internal multiplication of measures. We are producing a new measure, which we have called mu1 star mu2. It's the measure which by action, and now the second application to f, is giving you the same as the iteration of these measures, which is mu1 first applied to f, which is apply the convolution operator from the functional mu2, and then you have a new function, I put brackets around it, and then you convolve with mu1. So this is an iterative procedure. And by showing that this is a commutative thing, we can say that this is the same as mu1 convolved with f, and then from the outside convolved with mu2. But of course, sometimes the measure may be coming from an ordinary function. All the measures may be coming from an ordinary functions. So some of the stars could be, I don't know, pointwise multiplication of convolution of functions, or one is a measure and the other is a functional. And we want to discuss this issue, I mean, once for all, so that we can use them freely as much as you're using the multiplication of numbers. Now, one thing which I was using already is implicitly was lemma 9, which says we have first the approximation of the convolution operator by mu by discrete version of the measure. And now I'm concatenating two discrete convolutions and apply them to some function f. And this can be written by the red formula as the concatenation of two actions of measures on functions. But in their action, this is going to the convolution operator. Now, in particular, this implies that we have this weak star convergence, which means that you're not applying it to f, but to f flipped and evaluating at 0. So these measures are weak star convergent to mu star nu. So if I use the arrow with the weak star, the first weak W symbol should be erased. Now, this was the consequence that we have used already, and the proof is quite easy once you are writing it in terms of operators. So we want to control the action of the convolution operator, which is arising from these discrete measures to the f and versus this continuous convolution in a way. And as usual, it's the same proof that you would use to prove that a times b is close to a prime b prime. If a prime is close to a and b is close to b prime, you insert an intermediate term, either a prime b or a b prime. So we're saying we shouldn't change both of them from the discretized measure to the non-discretized, but maybe we keep the discretized measure mu, and we change from deep psi nu to nu. So we have inserted an artificial term minus deep psi mu, nu star f, but because we can change the order now, we can pull out the nu and write it now. We have to correct the deep psi mu should go to the mu. So if you add up those four terms, you see it's a telescopic sum, and it has exactly the sum is what we have here, but we apply the triangle inequality. The subnorm of the sum of those two functions is at most the sum of the infinity norms of these functions. But now we can apply and say, okay, distributive law, this is deep psi mu applied to, on the first hand side, we have the discrete nu with f, and here we have the continuous nu with f. So you have only a difference of the form that we know will go to 0 if you make psi fine enough. And in the second, and we have pulled out the nu now, that's a fixed number, you have a rest which is coming from the discretization of the mu. Now, the only kind of bad thing here is that the left-hand side also depends on mu, and that's why we have to recall that the discretized measures have a mass, a total norm, which is at most the mass of mu. So we have the measure of mu can be here in the last line of page number 30, times something which is getting small by making psi fine, and the second one is the size of mu, and the mu discretization is going to work well. So we see that we can make this arbitrarily small, and of course, if you want, you could choose different partitions of unity, phi and psi, and have the same effect. So it's just whenever you do these convolutions, you have this. I would like to mention that if you're trying to convolve, let's say, two Gauss functions, and you're making an experiment, you would come up with a histogram. Now, a histogram is very much like the information that you have in a deep psi mu. So you're saying you have bins and they're over intervals. So what is the probability of getting into some interval? And then you're saying, well, I have two experimental data, two probability distributions, but you only know the deep psi mu and the deep psi nu from the histograms. And then, of course, you will say, well, I convolve the data that I get from the histogram, so discretized data. And what this is telling you that in the weak star sense, so when you apply it as a convolution operator or later on just to a test function, you're getting almost the same as you get by doing this continuous abstract convolution. And that might be the convolution that you find in the books or so, but we will see it's always the same convolution. Now, in order to specify, and this was the form how we were using it, that we have weak star convergence, we have to look at the difference. So we look at this discrete convolution. So it's a really internal convolution of discrete bounded measures. And then the result is applied to some function f. And now this translation formula, we translate it back to systems. It's just put a flip into the system generated from the bounded measure and evaluate at 0. But because we have now that the whole operator goes uniformly, the specific result of evaluating at 0 must work. And therefore we have, it's going to mu star nu, the bounded measure, which is defined in the classical, in the way of composition of operators, applied to f. And so if we use it in this way, then we can have all the arguments in place that we were using for the proof before. Now, I will maybe use another fact, and because it's just here now, I will do the proof. It's a one-line proof again. I mean, a very dense, very compressed one-line proof. And again, you could write everything with integrals, and you would have a one-page proof. I'm just telling you that if you take a function and you flip it, if you take a measure and you flip it, and it was the action of a measure, a flipped measure, well, it's just the flipped measure on f is just the same as the measure on the flipped function. Why is this reasonable? Try it out and try to find what the flip of a Dirac measure is, and you will find it's the flip with the negative argument. So it's delta x flipped is delta minus x. Okay, so we have now the game. Measure nu can be acting by convolution according as a system on a function f, a Bibos system, and then you can flip the output, or you can put the flipped input and you convolve with the measure which is the flipped measure, and the claim is this is the same. I guess I have tried to make it in a two-line proof. What you need is f double flip is f. So if you flip twice, it's minus x is plus x. And if you flip a shifted function, it's just a shift to the negative thing. So just write down argument tyf flipped at the point z is what you have here, and then you are. Now, applying, and that's more an exercise on really using the facts that we have already established. Convolving a function named f flipped with a measure nu flipped at a point f means you have to take the measure nu flip, and then you have to insert ty of the input function flipped, but it's f flipped flip, and that's why you see there is just an f. So we have this here. But what is the action of a flipped measure on any function? It's just the measure applied to the flipped input function. Now we use the translation rule. It's t minus y of f flipped. And so you see, oh yes, it's nice. It's of the form a functional applied to a shifted version of f flipped. So it's a convolution of nu with f, but the argument is not ty, but t minus y. So it's nu star f minus y. But nu star f is a function, and the flipped function at the point y is exactly what we have here. It's a minus y. So this will be used later on, but it's a very natural thing. You're convolving operators and you're flipping functions. And essentially, you could use such an argument to show that what I told you about convolution without or with flip, it's not a big difference, because we're using, in order to be consistent with the books and with the mathematical literature, the flipped version, because then convolving with the Dirac at x is the shift operator by x. If we would throw away the flip, we would have the same composition law, but we would have a composition law where the moving average with respect to a Dirac measure x is describing the t of minus x. This was more or less the kind of slightly more simple situation that we were discussing for the polynomials. Okay, so this is something quite technical, but the point is the technicality and is made such that you can use it anytime later on, and we're never considering that there's a big difference between pi times 1 over pi or 3/4 multiplied with 4/3. So we always think, yes, we divide through, we cancel out, and that's what we will do here. Okay, so yeah, here is the concept will be, or the question will be now, what can we say about different kinds of convolutions? And we have seen now, we can take a function k1 and another function k2. And if you're asking me, how can I convolve this? There are different ways of getting another function. You can say, well, I do it in the pointwise sense. So this is meaningful. And this pointwise convolution can be shown to also have the same properties, meaning shifting one of the two functions is the same as shifting the output. This is a good exercise and worthwhile. On the other hand, you can say, no, at the beginning, we only know how to convolve a measure with a function, but we can turn one of the guys, let's say k2, into a measure, and then we can apply this bounded measure with density k2 and convolve it, or let it act as a system on the input signal k1, or we can change the role. If we go to the measures, we can also do different things. We can say, well, two functions are giving two bounded measures. This composition in the first term here in 62 is a convolution of two bounded measures. It's a measure. Or we can say, well, the pointwise convolution of two test functions, k1 and k2, is giving another continuous function with compact support. So we take that pointwise product and make a measure. Well, actually, it would be a disaster if this measure would be different from the product of measures here. But you see here, the measure product is in the sense of composition of systems, whereas here by integrals. I think by showing that these two things are the same, we have a motivation why this funny integral is so reasonable. It's helping us to concatenate two systems, both of which have a density. So maybe you have a moving average. The moving averages takes an average over an interval of length 1. So you're integrating a function on the real line, a continuous function on the real line from x minus 1/2 to x plus 1/2. So because it has length 1, you don't have to divide it through. And then you iterate and you do it once more. And of course, you know this should be the same as a moving averages with a triangular profile. And the triangular profile is starting from x minus 1 going up to x plus 1. And it's just because a box function convolved with a box function in the pointwise sense is a triangular function. Of course, just to confuse you even more, and make it more systematic in a way, we could take the measure coming from one of those functions. But if you know already that these three functions are the same, you can replace the pointwise induced measure also by any of the others, and that will be no difference. I also wanted to mention that we are not claiming that discretization is completely compatible with convolution. So we have seen it's only approximately, so you cannot say that the discrete version with a psi or even another psi of mu1 convolved with mu2 is the same as the composition of the discrete measures. So we have to be careful about this here. So let me see. The first one is what I will write later on as mu. Yeah, I made a shorthand notation. We have two continuous functions, k1 and k2, and therefore it's natural to call the measure induced by k1 just mu1, and the measure coming from k2 I call mu2. So one of the versions that we have is take one, make it into a measure, and apply the convolution operator in the sense of a system applied to the k1. Now we have a rule which is quite clear. How can you get the output of a system induced by a measure at a point y? And the rule is you're taking the measure. And so you look at this integral and you say, I'm first writing integral RD, and then the measure is k2 of set d set. And you apply it to the input function, first flipped and then shifted by the argument that we have in mind. So we have to take the input signal k1. I put a little bit more brackets to avoid confusion. And we take the flipped version of k1, then we shift it as a function of set. It is integrated, is undergoing an integration against the functional. So it's mu2 of this shifted flipped version. Now we have to spell out what it means. A shifted version of any function, here it's k1 flipped of set minus y, is just the shifted version times k2 of set. But the flipped version of k1 is just k1 without a flip at y minus set d set. And that's exactly the definition of the pointwise product. And you see here also, I mean, if you learn about the convolution for functions, you can usually, and if I would be in a live situation, I would take the graph of two such functions, I would put them on old overhead slides, I would flip one, which means I put it back, you look at it from the other side, and then you move it along the translation parameter, take the product functions and integrate. But this is the pointwise. So by this one-line proof, we have seen that you can take a measure, take a density, turn it into a functional and apply the mu k2 on the k1, and it's exactly a function which you could get directly by pointwise multiplication. The next thing is, I'm probably repeating myself. Oh yeah, no. It's the question. It's now the first question. Maybe I'm going back to my slide. So we have identified the mu k2, k1 with the pointwise convolution, and by symmetric changing the indices, you get the same. So these three functions are equal. So we have to concentrate now on the question whether pointwise multiplication, in the sense of pointwise convolution by an integral, by a Riemann integral, or composition of systems is the same. So we have to try to understand this. Maybe we can do it in a shorter way, but I was recalling again that, well, let us call the product, for simplify the notation, mu1 with mu2 convolution. And there's the other guy, which is the measure introduced by the continuous test function arising as pointwise product. And we want to show that they are the same. I must admit that I was writing quite a few pages with pencil, and so kind of it's maybe you have to get used to it, but by demonstrating it how you can build up the argument, you see I'm always using the same argument. So at the end, to verify it's not difficult to kind of put things on the side and reconstruct it. Even for myself, I need some concentration to do it. So I hope my write-up is giving you a reasonable way of doing it. So we want to show that the, question in the chat. Yeah, I will do a correction. Okay, so thank you. If you have the measure mu, which is the convolution product, the rule was that we have to take the convolution operator applied to k flipped at 0. Now we have to insert the definition of what does it mean to take a product of convolution operators. It's applying a convolution operator and then another convolution operator. So it's just redescribing the action of the product operator of the product of the two systems is apply one of them to k flipped, and the result is put into the next system mu1, and the combined output of the serial description at 0. Now we have already seen that C mu k upon. Now we use the definition of what the system mu1 is doing. It's taking apply this. I'm seeing now. Apply this and evaluate at a 0. So there is a 0 missing here. So we do this. So now we have to look at the description, and I'm continuing now from 64 to 67. So it's C mu of C mu2 of k flipped, and so at 0. Now, okay, yeah, now I see. 66 is an evaluation, which is more or less what we have just done, but with a flip operator. So maybe I redo it. System output on k flipped on y is you take mu2, the generating functional, applied to ty k flip. So it's tyk, which is this integral, but we would like to write it as an integral where it's acting on the k, and that's what you get by substitution. Replace set by set plus y. So instead of argument set for k2, you get now the argument set plus y. So you have this formula, so it's more or less a plus instead of a minus in the pointwise convolution relationship. But there is one more flip. So we have this outer flip, the second flip in 67, which turns everything back into a minus. So we have this, and now we have 3 functions, all of them continuous functions with compact support. And therefore we can apply the ordinary Fubini. It's just saying that the volume of a rectangle is a product of the side lengths, and you can choose any order. That's for step function then, and so on. So we have changing the order of integration. So instead of d set dy, we do choose dy dz. And so you pull out the k, and what you see here is the remaining input, and that's just exactly the pointwise product. So if you kind of recapitulate it, it's just, and maybe you can find an even more short and elegant proof, but it's saying the action of a functional is obtained out of the system. A system corresponding to a convolution product, by definition, is the concatenation of the systems. And then you play around, what does it mean in the concrete context? You apply translation, so a change of the parameters, and you're applying a Fubini theorem, and you're coming up that now we are integrating k of z, the input test function, against some function which has compact support. Now, once you have established this for every function k with compact support, you know that both the measure can be extended to any f in C0 by approximation, and also the integral is meaningful because this is a continuous function with compact support, which can also be integrated against the bounded continuous function. Therefore, k can be replaced by f in C0. So you have mu of f is just the action mu of pointwise product applied to f for every f in C0. And this is kind of what we were going to do. So we have now, in a nutshell, tried to concentrate on different ways of taking functions, convolving them either by turning one of them into a measure and applying the action of a system with a density to a test function, or do a pointwise integration, or turn both into measures and compose them, all these concepts are the same. So I would say that from now on, using a star, and instead of writing T for the system arising from the measure, or so we can always use the same star, and suddenly, I mean, the associativity is kind of a harmless question with multiplication. It looks like a harmless thing, like a multiplication. Okay, the next direction we go is to try to prove the convolution theorem. So we will see that the composition of convolutions is corresponding to a pointwise multiplication of the Fourier transform. As already indicated, we could do it for L1 using Lebesgue integration theory. We will do it for bounded measures, but then we need to prove that it is okay to extend the action of a linear functional on C0 to the bounded measures. So sorry, this red formula now, number 80, is a good thing that is quite well justified. And even if you have 3 signals and you don't know which one should be a measure, you don't want to fix the order, all these things are okay. I would like to warn you, but as a warning at a very high level, people who are doing distribution theory and who try to define convolution in the most abstract way, I mean individually, not by composing operators where associativity is kind of obvious, but individually, they can show that there are generalized functions, temporal distributions, where this law is kind of not valid anymore. But I'm convinced that these situations are pathological situations and are not relevant for engineering applications. So I'm now talking like an engineer. Now, to go in the direction of bounded measures, I'm coming now to, because I think it's just enough time to do it now until the end of the lesson. I'm trying to convince you that you can extend the action of a bounded measure to all of the bounded measures. So I'm replacing C0 to CB. And maybe I will tell you later why we don't take CB as a starting point. There are good reasons to work with C0 first, but once we have about the linear functionals, and we have certain properties of these bounded measures, we can extend them to the bounded continuous functions. So in order to define the Fourier transform, we will have to integrate a pure frequency against the measure, and clearly a pure frequency is only bounded, it's uniformly continuous, but it's not decaying at infinity. So how can we extend a bounded measure to the bounded continuous functions? So you're giving me H in the bounded continuous functions and some measure and say, how can you define it? You cannot approximate this maybe constant 1 in the norm of the sup norm by functions vanishing at infinity. This is a closed subspace. But what you can do is you can split your function into pieces. So you can think of mu as being the sum of the mu psi I. And therefore it's plausible that you can define mu of H as mu of psi I times H. If you're looking at this in a very pedantic way, we have to do a lot of things. For example, which I didn't write down, is this kind of new definition independent of the partition of unity? So if somebody comes and gives you another partition of unity, would you get a different result? Answer, of course not. If you take a function which is some f in C0, so something that you know pretty well what it is, do you get some new value? And then, of course, I would say, no. F is the sum of the psi I times f. So it's the sum of the local pieces. It's not absolutely convergent, but it's adding up as a limit. So you're getting, you change that mu of the sum of the pieces is the sum of the mu of the pieces. So you can be quiet, and this is really an extension of the old definition. But before or instead of going into this discussion, we have to analyze whether this is meaningful. So is it really possible to do it? We have to recall this very important property that has been used already before. For me, this is the replacement for sigma additivity. So the sum of the pieces, which I call mu psi I, measured in the measure norm over the index set, typically a lattice, is the same as the total mass or the size of the measure. Also, for some trick that I would like to apply, I will use some functions psi I star, which is reproducing the psi I. So if you think maybe this psi I is a triangular function at any position, take a trapezoidal function, which is a constant 1 on the support of the psi I, but a little bit larger. We will use this psi I star in a more concrete form later on, but you can take, for example, the sum of all the psi j's, the neighbors, which are non-zero product with the psi I. So essentially you're saying psi I is 1 times psi I, but then you're writing 1 as a sum of the neighbors and throw away the ones which you don't need. So it's very easy to reproduce. And the point is, if you think that the psi I are obtained by shifting, so maybe the shift triangular functions, and psi I star is a trapezoidal function, you just shift the trapezoidal function. But we only need that for any function with compact support, whatever it is, you find another function which has bigger support, of course, which has supernorm 1, which reproduces the given one. So that's a very harmless property. So how can you estimate the action of mu psi I on the function IH if it's given by this? Okay, there is a less or equal missing in the 89. So I have to look at the pieces, and now artificially I want to get out this, use the size of the mu psi I, but then it would be applied to H, which we cannot do, but I can insert the psi I star. So the good thing is here, if I write psi I times H as psi I times psi I star times H, each of the functions psi I star H, has compact support because the first factor has compact support, and it's also bounded by the size of the H. So of course, this is an absolute value of a kind of localized functional applied to a localized test function H in the bounded domain. But by the standard estimate, you take the size of the functional times the size of the function. But each of those pieces is definitely not larger than the supernorm of H. So these psi I star H norms are uniformly bounded with one constant, which is the sup over the H, which you can pull out. So the remaining part is the sum of the psi I, and we have seen that this is true. So for every, following the definition, for every such H, you can estimate it by the supernorm of H times the measure norm, which means it's a bounded linear functional, and the norm doesn't exceed the norm that you have already on C0. So we have extended a linear functional from the small closed subspace C0 to the larger space of bounded continuous functions. We have seen that the supreme, the action norm, is not bigger, but of course it's also not smaller because, I mean, C0 functions are still available. So we have, as a functional on those bounded, it extends in a unique way to CB, and we can control it, so we have an operator norm. Now, I only tell you a story which we will do later in more detail, because we will talk about approximate units. Here we have used partitions of unity, and we were writing an infinite sum, and of course the infinite sum is the limit of finite partial sums. So for example, take this again system of triangular functions. I will show you similar things in MATLAB so that you get a more intuitive understanding. The partial sum of triangular functions living on minus n to plus n would be more or less a trapezoidal function, constant 1, let's say from n minus 1 negative to n minus 1 positive, with some side lobes. But you can take other functions which are having this property, so larger and larger plateau functions. And so by just multiplying your h with C0 functions, you would keep the main part intact, but you would be able to show that this limit exists and is the same as the mu of h that we have taken here. Roughly speaking, you can also think, well, most of what happens with the action of mu is happening in a compact domain. So a finite partial sum is doing 99% of the action. So if you just cut off the tails, it's not changing very much. So this will be another way, but in order to show that for different approximate units in C0, you get the same limit would probably be more cumbersome. I have kind of as an exercise, I have tried myself to show that this definition is independent of the partition of unity. That's kind of half-page proof. I will probably insert it into the script, but it's important that you can define it. Now coming to the Fourier transform, which is our next goal, is we recall that the Fourier transform is usually defined in this way. You're applying, you're multiplying the function with a pure integral. For those who know already the scalar product in L2 or in the torus, where the domain is a finite domain, you will say, oh yes, he's integrating f of t against the conjugate of a pure frequency of the form e to the 2 pi I omega t. And the conjugation for exponential function is, of course, the minus. So I'm preferring, of course, the complex notation, but you can apply Euler's rule and write cosine plus I times sine. And I will do everything without kind of noticing very much in the d-dimensional, multidimensional setting. It will be useful to do it, for example, for image processing. But if we want to generalize it, it's plausible that we have to read this as, no, it's not f of t multiplied with a pure frequency, but it's a symbol which is occurring like integral of Rd applied to e to the minus 2 pi and so on with density f of t dt. So it's apply the measure coming from the density against the conjugate of a pure frequency. But this is a nice thing. So I think I'm afraid that I have not transferred it from the script to this extra script. But maybe I just tell you what we're going to do. So we will define a Fourier tilde transform by applying the measure, which is now extendable to bounded continuous function, applying to the conjugate of the pure frequency. And the corresponding expected convolution theorem in this context will be f of a composition of two measures is the same as the Fourier transform taken individually in a pointwise sense. Or in other words, if you use just a hat for the Fourier transform, mu1 convolved with mu2 is just the pointwise product. So the goal will be really to show that composition of systems is going to a composition of multiplication. So actually we have to discuss, and that will be the subject of Thursday's course, we have to see that these measures, usually appearing as impulse responses, correspond on the Fourier transform side to multiplication with certain operators. Therefore, the composition of such things is a composition of multiplication operators, which is, of course, multiplication. So later on, we will use the terminology mu is the impulse response of the system, mu hat is the transfer function, and of course, if you multiply the transfer functions, you're having the effect of the multiplication. It will be also important to see that, of course, different systems have different transfer functions. So this extended Fourier transform or Fourier-Stieltjes transform defined on the bounded measures is injective and turns convolution into pointwise multiplication. So the multiplication inside of the bounded measures, which we have defined, is going into the multiplication in the range. I also forgot to mention that for each bounded measure, we're getting a bounded continuous function. That's one of the reasons why also working with the algebra of bounded continuous function was at the beginning of my course here. We will see that this is an injective procedure, so different measures define different systems, and of course different systems have to correspond to different multiplication operators. And now it's not just sets of measure zero. Two transfer functions are different, which if they are really different, at least at some small interval or some open set or so. I think I will stop here, but maybe give you some indication. Yeah, chat. Yeah, so maybe I should indicate if I talk about this here, we have learned so far that pure Dirac measures. So this is as a function of the point evaluation at a given point. The Dirac at zero is the point evaluation at zero. So it's nothing mysterious. It's just a linear functional described very easily. The same Dirac that I was using for the cubic polynomials or so. And if you turn them into a system by our recipe, you get a translation operator. From this, we got that the convolution of Dirac measures is giving you another Dirac measure with x plus y or so. Now, what we will have to do is to understand much better what the Fourier transform of a Dirac measure is. And we will see that I mean, you probably know the rules that shifting a function corresponds on the Fourier transform to multiplying with a pure frequency. Or the other thing is, if you hit on your keyboard the transpose key, so you don't like, I don't know, a complicated tune and prefer to play in C major, then you press the transpose. That means the sound that is produced is multiplied with a pure frequency, because multiplying with a pure frequency corresponds to a shift. So we will see that the Fourier transform turns Dirac measures into pure frequencies, and in the later we will see extended way pure frequencies are turned into Dirac measures. So this formula, the convolution theorem, is valid in full generality, but we will see later on, for example, we cannot deal with bounded measures when we are interested in translation invariant linear operators from L2 to L2. We need to extend the setting furthermore. But this theorem will be valid. So whenever convolution is meaningful, it should be true that the Fourier transform can be applied and pointwise multiplication is meaningful, and vice versa, because we should be able to come back. So we will use this many times. So of course, we're at the cumbersome part of the course where we do a lot of theory to reach the freedom that we need to justify all these manipulations with convolutions, changing the order, replacing things, putting kind of nasty objects, including Dirac combs, into these formulas, and everything will be justified. And I think that's kind of my great goal. I think it's a good point to stop here and start preparing for the next course. So please ask questions right afterwards. So I stop.